Good time of the day. Welcome and thank you for joining the 102nd webinar in the GIF Education and Training series. This webinar is titled Thermal Hydraulics of Supercritical Pressure Water-Cooled Reactors. So first I will go through a few housekeeping slides. So you can please use the sound from your computer when given the option. If you have any technical issues, look for help on the Zoom Assistant webpage. It is indicated here. The recording and the presentation of this webinar will be made available later on the GIF public website in about a few days after the webinar. Please share the information about this webinar to your network. And most importantly, you can ask questions throughout the webinar using the Q&A function. I will show you in a second how to do it. Your questions will be visible to the speaker and the moderator, and we will make sure to answer them after the main presentation of the webinar. So thank you again for joining. And I would like, just a quick point on the Q&A function. You can see at the bottom of your screen, there is this Q&A button. If you click on it, it will open a pop-up window where you can type your question and send it to the moderator and the speaker. And once the main presentation is over, we will take the time to answer live those questions. So I would like now to introduce the moderator of today's webinar. Dr. Patricia Pavier is the National Technical Director of Molten Salt Reactor Program for the US Department of Energy at the Office of Nuclear Energy. She's been an active member of the GIF Education and Training Working Group since the inception of the group. And she was actually the first chair of this group. And she is now the webinar lead for the Education and Training Working Group of GIF. She's been instrumental in establishing the present series of webinars with more than 100 webinars streamed since it started. And she keeps it flourishing with the energy and enthusiasm she puts in it. She will facilitate the webinar today and the Q&A session. And I will let now Patricia introduce our main speaker for today. Patricia, the floor is yours.
Yeah, thank you so much, Alexei. Good morning, good evening, everyone. It's a pleasure to welcome Professor Xiaojing Liu from Shanghai Jiao Tong University in China, who is going to present this webinar. He obtained his PhD degree from this university in 2010, and he was a postdoctoral fellow at the Karlsruhe Institute of Technology in Karlsruhe, Germany from 2012 to 2013. He's currently the director of the Shanghai Integrated Innovation Center for Digital Reactors, leader of the Innovative Nuclear System Laboratory in Shanghai Jiao Tong University, and he has long been engaged in research on advanced and digital nuclear energy systems. He has published more than 200 papers in renowned journals such as Applied Energy, Energy Conversion and Management, and Annals of Nuclear Energy. He serves as a board member of the Nuclear Reactor Thermal Hydraulics Division of the Chinese Nuclear Society. He's associate editor of ASME Journal of Nuclear Engineering and Radiation Science, editorial advisor board member of Nuclear Engineering and Design, and youth editorial board member of the Nuclear Science and Techniques and Frontiers in Energy. So without any further delay, I give you the floor, Professor Liu. Thank you very much again for accepting to present this webinar. Thank you very much.
Thank you very much, Patika, for the introduction. And hello, everyone. Good morning, good evening. I think this is a very honor to be invited to this presentation. And today, the topic of my presentation is thermal hydraulics of the supercritical water-cooled reactors, SCWR. So here, firstly, I will show the one picture of the SCWR, and you will see that the pressure of the SCWR is about 25 megapascal, and the outlet temperature of the fluid is over 500 degrees C. So at that time, you will see in the right side is, the properties of the supercritical water. You will see that. And density here shows a very sharply decrease when the temperature is over the pseudo-critical point. And you also see that the conductivities, Prandtl numbers, and also the thermal expansion coefficient, every properties will go through a very sharply decrease or increase or some very big change. So this is, I think, bring the challenges for the design or for the operation work of the SCWR. So this is the key point. The pressure, high pressure, and the high temperature is one of the most important, the thermohydraulic characteristics of SCWR. So I will give you the introduction for the SCWR, and you will see that from the picture I show you last slide is very simple and compact plant systems. It only has one loop. They didn't need the secondary loop and steam generators like BWR. And also you will see that because when the water is on the supercritical condition, there is a one-phase flow. So in the one-phase flow, we don't need the water-steam separation, and all you can see that the thermal conductivity and also the CP of the fluid is very high compared to the ordinary water, and you see that the SCWR, he needs a very low flow rate, and you will see that is about 1/8 to 1/5 of the compared to the current PWR. So they have the very high enthalpy coolant. And also you see that the very high temperatures over 500 degrees C, they can get a very high thermal efficiency is up to about 44%. And you see that the density of the supercritical water can be decreased from the when the temperature across the critical points. So it can be realize the flexibility of the neutron spectrum, because if the density is decreased, you can design your reactor like faster or thermal spectrum. I will show you in the later slide. So that maybe is that if you use a faster spectrum, so you will increase the utilization of the fuel. And also, if you see the picture of the SCWR, this is the combination of the current light water reactors and the supercritical fossil power plant technologies. And also the major components are used within the temperature range of the past experiences. As you will see, there's a lot of advantage of the SCWR. And here I give you a table that to summarize the comparison between the PWR, BWR, and our SCWR. So from the features, you will see that for the system structures, the PWR has 2 loops and the BWR 1 loop. And also you can see SWR, they have only 1 loop. It's very simple. And for the flow path in the core, that's the PWR has 1 through, and BWR has a recirculation loop. And also you will see the SWR, they have the multi-pass coolant flow in the core. And if you see the flow direction in the core part, in the PWR is vertical upward, in the BWR is also vertical upward, but in the SCWR is up and down. So this is maybe bring some challenges to the thermohydraulic design of the SCWR. And also you will see for the semi-hydraulic parameters, for the PWR, he has the subcritical and the subcooled boiling. And also for the BWR, you will see it's also subcritical pressure, but as very high void fractions. And for the SCWR, as I told you before, is supercritical. When the water at the supercritical condition is only one phase. There's no phase change during the supercritical point. And also for the pressure, the operation pressure, and in the PWR is about 15 megapascals. For the BWR is 7 megapascals, and for the SCWR is 25 megapascals. And for the temperature, you will see that for the both the PWR and the BWR is below 330 degrees Celsius. But for the SWR, the coolant temperature in the outlet can be over 500 degrees C. And also for the mass flux, you will see the PWR has very high mass flux, and the BWR is mean the medium, and SWR, because the coolant has very high enthalpy, so that they can get a very low value of the mass flux. And for the geometries, you know the geometry of the assemblies, and the PWR has very large field assembly, BWR has a small one, and the SCWR have the both large and small ones. And also for the lattice is the square and white for the PWR and the BWR. That is for the SCWR, we have used the semi-tight lattice for the field design. For the spacers, both BWR and PWR has the grid spacers, and for the SCWR, we use the grid and wear grab. And also for the moderator channels, for PWR, we don't need moderators. For BWR, yes, we have some of the moderator channels, but for the SCWR, because you know the density of the water is decreased sharply, so they cannot provide, the enough moderation for the neutrons. So we need the moderator channels. And in the moderator channels in SWR, they have the counter current flow in the different directions. In the vertical directions is downward, upward. And for the design criteria, you know that the field temperature and the CHF is the design criteria for the PWR and the BWR. But for the SCWR, you know that I told you there's only one phase flow in the supercritical condition. So that means the temperature, the cladding temperature, surface cladding temperature will be the design criteria for the SCWR. So this table summarizes the comparison between the PWR, and SCWR, and you will see that the thermohydraulic properties can bring a lot of advantage for the SCWR, but in the same time, it also bring a lot of challenges for the SCWR, such as the multipass, the counter current flow in the moderator channel and the coolant channels, and also the very high pressure and very high temperatures of the coolant. And also we have the tight lattice for the field assemblies. Both of this, I think can bring a lot of challenges for the thermohydraulic design for the SCWR. And so from that last table, you will see that we have the extremely operation conditions. That means we have the very high pressure, high temperature, high flux, and also we have the neutron radiation, and this will bring the challenges for the core and the field assembly designs. And you will see that it has large property variations, especially during or near the critical points or procedural critical points. And also we have the non-uniformity of the moderation, and also for the sensitivity to the hot channel factors. And because we have the tidal lattice, so the non-uniformity of the local heat transfers, and we have the tidal lattice, or we have the wear gaps as the spacer. So the blockage of the bundle will be a very serious accident during the operation. And also the upper limit of the cladding temperature is the design criteria for the thermohydraulics analyze or design of the SCWR. So these challenges bring a large number of field assembly FA and core designs. And here I will just show you, I will call back the flow properties variation between the when the temperature across the critical or the procedural critical point, that means the point 1 in the XL, you will see this very sharply variation of the properties. And at that time, we need the moderator channels in the field assemblies. And the next slides, I will show you the different core designs and the conceptual design. And the 3 kind of designs. The first one is from our European partners for the thermal SWR design. And you will see they use 3-pass design. That means the coolant entering the pressure vessel, and they will downward, and in the lower part upward, and then in the middle part downward again, and then in the outer part is upward. So by this 3-pass design, and the coolant will be heat up 3 times from the reactor core, can be heated to the 500 degrees C. And also you will see, because it's a thermal design, so they need some moderator channels inside the field assemblies. And another design is Japan faster designs in the middle. So in this kind of designs, you will see that because it's a faster core design, they don't need the moderator channels or moderator box again, but also the flows will be inside to the pressure vessel, downward and upward. And in the upper plenum is go downward to the lower plenum and heated, and then in the seed assemblies is heated again. So that's a 2-pass design. And the third one is developed by China, by our university, is a mixture spectrum design. We call it the SCWRM. And at that time, the inner part is a fast zone with the field assembly like this one. And in the outer part is the thermal zone. In the thermal zone, of course, we need the moderator channels. And the coolant will be into the pressure vessel, is upward, and then firstly go downward from the thermal field assembly, is heated up and mixed in the lower plenum, and then upward again from the faster zone. The advantage is that in the when the water enter into the pressure vessel is in the low temperature is low, and the density is high, and then they can provide enough moderation, and then we can get the thermal spectrum of the neutron. And when the temperature is over the critical point or the pseudo-critical point, and the density of the coolant will be decreased to a small value, and then it can't provide the enough moderation, and then okay, we can design it to the fast spectrum. So this is the conceptual ideas of the different designs, the thermal designs, the fast designs, and the mixed designs. And here you will see that when the the SCWR, usually they can operate it at the supercritical condition. At that time, the temperature is over 500 degrees C, the pressure is over 225 megapascal. And at that time, there's a single phase, there's no phase changing in the core, no boring increases like PWR and BWR, both of them has the DMB or the drought effect. But for the supercritical water reactor, when it operates on the supercritical condition, there is only single phase and no boring increases occurs. But during some transients, such as the setup phase or the shutdown or the local accidents, and you can see from the right side, and the temperature will be goes through some transcritical transient. So what's transcritical transient is it can be decrease from the supercritical condition to the subcritical condition, or maybe the pressure will increase from the subcritical condition to the supercritical condition, and this transient can bring a lot of challenges when we um, perform the thermohydraulics analysis for the SWR. So after the introduction, and I summarize the advantage of SCWR and also the challenges for the thermohydraulic point from the thermohydraulic point for the SWR. So I will go to the next one for the supercritical condition heat transfer. In the past years, we have established a heat transfer data bank to supercritical fluid. It contains experiments of critical fluid flowing in vertical tubes, including more than 80,000 data points from 3 different fluids, like water, freon, and CO2. And as the table shows, the range of the conditions covers in our data bank for the supercritical water. So you will see the system pressure is range from the 22.3 to 41 megapascal. And for the mass flux, the experiments span from a very low value around 100 to 3,600 kilogram per square meter seconds. And the heat flux goes from 0.1 to 9.4 megawatt per square meters, and the tube diameters is from 1.3 to 46 millimeters. And for the for the for the phenomenal point of view, due to the large variation of the thermal physical properties, especially near the pseudo-critical line, there exists a strong buoyancy effect and acceleration effect near the heated wall. The acceleration effect can be characterized by the density gradients in the main flow direction, in the z direction. Therefore, we introduced a new dimensionless parameter with, like this one, the pi a. We call it the acceleration number, and it's proportional to the different parameters like the expansion coefficient and also the heat flux and also the CP and also the mass flux. And furthermore, the buoyancy effect can be characterized by the density gradients in the radial direction, in the arc direction, and it can be expressed by the pi b. And for the simplicity, we simplified the expression with property parameters based on the back temperature. Therefore, the new dimensionless parameter expressed by the acceleration numbers, Reynolds numbers, and Planck numbers is called the buoyancy numbers. We take the following criteria to derive the final structure of the correction factors. I mean, to calculate the heat transfer coefficient in the supercritical condition. Firstly, the correlations should be based on the dimensionless numbers so that it can be extended and applied to various, the different supercritical fluid. And the second is correlations should contain as few parameters as possible, since the complex structure of the correlation should limit its robustness, especially in application to conditions near the pseudo-critical point. Thirdly, the correlation will cover both the normal heat transfer behavior as well as the case with strong heat transfer reductions, as about 50% of the test points in the present experimental databank, strong heat transfer reduction may occur. Sometimes we call it heat transfer deterioration. Therefore, the new correlation should be can be applied to all heat transfer regions. Heat transfer means the enforcement and the normal heat transfer conditions, and also the heat transfer deterioration case. The fourthly is the iteration process and the possible problems of multiple solutions should be avoided. So that means in the new correlation, the buoyancy, the boundary conditions only contains the heat flux, and the wall surface temperature is not, it should be avoided, because if you have the wall temperature in your correlation, and first you have to assume wall temperature, and then you calculate your heat transfer coefficient, and then you can see if the wall temperature is correct using the heat transfer coefficient. So at that time, the iteration will be you again and again that help you to achieve the exactly value of the heat transfer coefficient and wall temperature. And this sometimes can be cause multiple solutions of the wall temperature. Finally, based on the above mechanical analysis and the data bank, a new heat transfer coefficient correlation has been developed. It's expressed in the term of, you will see that it's very simple one. It contains the Reynolds number, Planck number, and also the acceleration number we developed before. As mentioned before, I think our heat transfer coefficient data bank contains more than 80,000 test points. So in order to access the model's prediction abilities, the entire data bank is applied as listed in this table. For every fluid, we report two metrics, and the mean error and the standard deviation, and you will see that the new model sets at the top. Notice for the water experiment, the present model we developed can achieve the mean error at minus, the 0.008, and the standard deviation at about 0.1 163. And for the Freon also shows similar low bias, only 0.035 in mean errors and 0.163 in standard deviations. However, the prediction accuracy for the new correlation is reduced if applied to the test data of the CO2. So compare with the other three different correlations with the given wall temperatures. So we compare with the Chen correlation, Bishop correlation, and also the Jackson correlation. Slight better prediction of the test data in water is obtained with the new correlation. Also, an improvement is observed for the prediction of the test data in Freon, whereas the previous correlation shows a much better prediction of the test data in CO2. All three correlations show the better agreement with the test data in Freon than those in the other two fluids. It is expected that the new correlation is more robust because it is less sensible to the calculation accuracy of the properties. And I think this work is still going on. If you look at the literatures in the website, there's still a lot of, the papers about the development of the supercritical condition heat transfer in different fluids. And another point is the scaling analysis, because you see for the supercritical water, the critical point is very high and the critical temperature is very high. It's not easy to perform the supercritical water experiments. So we can use the scaling analysis. So what the objective considered is the circularity tubes, the vertical direction, and the uniform heated, and the parameters to be separate controls during the, these parameters can be separate controlled during the experimental work. So that is tube diameter, the heat length, pressure, fluid temperature, mass flux, heat flux. And the parameters to be studied is the heat transfer coefficient or be the wall temperatures. And here is the scaling laws. We developed it here. And you will see that the required parameters in the prototype fluid, such as water, we can give the diameter, pressure, temperature, mass flux, and heat flux. And then we use the 6-dimensionally scaling parameters. We can use the scaling law, apply the scaling law to the different parameters, and then we can get the experimental parameters in the model fluid, such as CO2. And then, but it's a little bit easy to perform the CO2 experimental work. So we can perform the experimental work with the CO2, with the scaling parameters we derived from our scaling law. And then you can, after the experimental work, you can get the experimental results in the model fluid. And then we use the scaling law again, and we can scale our, the heat transfer coefficient in the prototype as water. So that's you will see that you perform the CO2 experimental work and you performed the scaling analysis, and then you can get the water heat transfer coefficient. So that will be a much reduce the cost of the experimental as much as possible. So after the development of the scaling law, and the most important thing is how to validate. So how to validate the scaled, the scaled heat transfer coefficients and also the experimental work. So thanks to the large data bank we developed ourselves with the 90,000 data points for the supercritical fluid. So we can check or we can select different fluid heat transfer experimental data, and then we can compare it. So we found 76 heat transfer points for Freon, and then we performed we can also find the accordingly the heat transfer coefficient in the water data bank. So you will see that we compare the scaled heat transfer coefficient and also compared with the experimental heat transfer coefficient in the water data bank. And you will see the average variation between the two different heat transfer coefficient is about 11%. And this, I think, 11%, this is in the acceptable range of the scaling analysis. And another point is I told you for the SCWR design, we use the tight lattice. For the tight lattice, I think the main figure is that the PD ratio is very small. So you know for the current PWR and BWR, the PD ratio is around 1.3 or even much larger. But for the SCWR, we use the PD ratio about 1.2 and 1.1. And at that time, for the tight lattice, there is a non-uniformity of the heat transfer. It can be found from the numerical simulation and also from the experimental work. So you will see that this is this is the angle 0. So that means in is in the gap region, and if the angle 45 is the white gap region, and you will see that the heat transfer coefficient or the Nusselt number is totally different. And if you see the cladding temperature, you will see that in the gap region, in the small gap region, the cladding temperature is very high, and in the white gap region, the cladding temperature is much lower. And at that time, we have to see if you use the tight lattice for the SCWR, you should analyze the non-uniformity of the heat transfer around the field road. So what we did, so we defined the local heat transfer coefficient and it divided by the average heat transfer coefficient, and we assume that is this non-dimensional number will be a function of the angle of the angle in the circumferential direction, and also the Reno number, Prandtl number, PD ratio, and a lot of the semiconductivities, dimensionless numbers. And then at that time, we can see that we can get the temperature distributions around each field rows from the angle from 0 to the 306 degree. And then we did some the analytical analyze, numerical analyze, and from the analytical analyze we get the dimensionless numbers, and from the numerical analyze we get the new models for the heat transfer coefficient, and after that we get the correlation as we showed here. So that you will see is a function of the angle and also of the function of the PD ratio, Prandtl number, and also the semiconductivity ratio of the cladding and coolant. So we take this heat transfer coefficient to the subchannels codes, and then you will see that it can be, to the simulate the, if you see the subchannels and if you wrote in the left side, and then you can see that we can the code can predict the local heat transfer distributions around one road. So you will see that the original, the Cobra or such other subchannel code, they can get only one value of the cladding temperature, such as the red line. But if you use this non-uniformity heat transfer models, you can predict the distribution of the cladding temperature or the heat transfer behavior around each field road. So to get very detailed information can be get. And even for if we use the var graph as the grid spacer, and then you need some, sometimes the blockage maybe occurs during the operation. So if blockage occurs, just block the the coolant channels. But you will see that if you perform the relap or athlete the system code simulation, if you get this very small region blockage, you will see that the blockage and no blockage, from the cladding temperature point of view, there's no difference if we perform the system code simulation. So what we have to do, we have to use subchannel code with the non-uniformity heat transfer models we developed before, and then we use coupled the system code with the subchannel code, and then we can get very detailed information when the blockage happens during the during the operation or the break of the var graph. And here is the common variables, the pressure, temperature, mass flux, and also the time steps, and also the coupled friction factors. And then you will see the coupling, the procedures between the system code and the subchannel code. And you will see from the cladding temperatures, and you see that the cladding temperatures, and you will see that the system code can predict the lowest cladding temperature, and also you will see the coupled or the subchannel analyze can get very much higher value of the cladding temperatures, and that shows, how important the non-uniformity heat transfer analyze is important compared to the thermohydraulic analyze. Sorry. Is the third part. I think we talk about the supercritical conditions, and then during some transients, we have some, the subcritical conditions. So we have to talk about the subcritical conditions, especially near the critical points. And you will see in the subcritical conditions, the boring increases maybe occurs when the heat flux reaches to the high level that we hit the surface can no longer support the continuous liquid contact, and the heat flux at the boring crisis point is usually referred as critical heat flux, the CHF. Since the poor heat transfer capability of vapor and the boring crisis could lead to the failure of the heated surface, therefore is a significant safety limitation to the heat transfer. Regarding to the flow boring in a pressure duct, and two boring crisis mechanisms are be supported to be considered, and one is departure from nuclear boring DMB, as shown in the left fingers, and another one is another kind of boring crisis is the drought. And I don't want to go to the detail of the DMB and the drought. I think this is a very fundamental thermohydraulics for the nuclear engineer. And the DMB usually in the low quality region for the PWR, and the drought is in the high quality region in the BWR. And both of these two phenomena can get a drastic temperature increase, and also to the challenges for the safety. And also the numerals of CHF prediction method has been proposed so far. They are rare of them regarding to the high pressure region. I mean that both of them is around 15 megapascal or 7 megapascal in the condition of the PWR and DWR. But if the pressure is increased from the 15 megapascal to the 25 megapascal, is still in the subcritical region, but the data is very, the number is very, very small. Therefore, we establish a new CHF data bank for the high pressure subcritical region, and currently experimentals with water and freon or CO2 as coolant are obtained. For each data point, it contains the information of the pressure, the mass flux, tube diameter, and also the critical qualities and the critical heat flux. And for the experimental with water as coolant, the data side contains 1,484 data points in total, and also a lot of the parameter ranges for the water. And for the high pressure freon data bank, it is make up around 1,000 data points with a reduced pressure up to 0.85. However, the high pressure CO2 data bank has only 2.8 data points with the reduced pressure from 0.8 to the 0.9. So that means there a big challenging, or we need a lot of data for the CO2 in the high pressure region. And the work to identify the key dimensionless parameters, and also we carry out for the DMB and the drought respectively. And for the DMB, I think we assume the boring crisis occurs when the liquid sublayer is drought, and we use the sublayer model and the Hall matrix instabilities and the dragging force and the buoyancy force, and we developed the DMB correlation. And for the drought condition, and we assume that the liquid film will be drought, and the evaporation rate equals to the deposition rate, and also the working of the evaporation force is equal to the turbulent kinetic energy of the droplets. And then based on these assumptions, we developed the correlation of the drought. And since the reliable distinguish criteria between DMB and drought is still unavailable so far, so these dimensionless parameters will be considered together. So we use the different group-wise statistic method is applied to figure out the most, the significant dimensionless parameters. So finally, it is indicated that the new CHF correlation is a function with the Boring number, Weber number, and also the critical quality written as, in the presentation shows us. And also we compared with different, the CHF models, and to compare with our models, and you will see that the present correlation gives a better prediction accuracy. And also the present CHF correlation as a dimensionless one developed from water experiments has potential to be applied to the other fluids. Accordingly, the predictive capability of the present correlation is evaluated and compared with other prediction method, and CHF experimental with different fluids. I mean, the mean error and also the RMS error with the Freon CHF experiments are very small, respectively. And for the, for the Freon, for the CO2, and after the boring crisis occurs, the post-CHF heat transfer region will be encountered, where the heat wall can be no longer be cooled by the continuous liquid phase. And also the post-CHF heat transfer data bank also has been established, and also to develop the new models for the post-CHF comparisons, and it can be demonstrated by the picture that the new post dry out heat transfer model could give a good prediction and is more accurate than the other prediction methods. And the fourth part, talk about some transient from the heat transfer during the transcritical transient. That means the pressure from the supercritical condition to the subcritical condition. And this part, is not easy to perform this transient because I show you the picture here. You will see that if we perform the transient, we have the saturation enthalpy of the vapor and the saturation enthalpy of the liquid. And at that time, if the pressure across the critical point, so that means the void fraction in the code will be get sharply, the jump from 0 to 1 or 1 to 0. So the numerical errors will be found and the code will stop working. So what we did, and we made the we modified the code, and we get the procedural region of the in this region you will see that, and in that region is also the void fraction in the supercritical condition also have 0 between 0 and 1. And at that time, if the pressure decrease from the supercritical condition to the subcritical condition, and you will see the void fraction, there's no, the jump from 0 to 1 or 1 to 0 is usually from 1 to the 1 to between 1 and 0 and to the 0. So at that time, it can be the code, it doesn't matter athlete or relap code, we can perform this kind of simulation. And after the modification, and we perform with our modified athlete code, to compare with our experimental work. And you will see that in the very high mass flux and low heat flux case, there's no wall temperature increase and there's no wall heat up. But if we see in the high flux case and even the experimental work, they can find the big increase of the cladding temperature. And you will see the yellow one is our modified prediction. And you will see that in the original one, they cannot predict the heat cladding temperature increase. But in the modified one, and you will see that there's a sharply increase of the cladding temperature. It can be agreed very well with the experimental data. And by the modified code, we perform the transient analysis for the SCWR FQT. This is a European project. It's called the SCWR fuel qualification test, and one fuel rod bundle will be installed in the test reactor in the Czech Republic, and the CVR, and then we have to perform the transient analysis of this the test loop, and is a full rod bundle. And here you will see that we perform the different locus. I mean, the inside locus, I mean, it is a cold leg or the hot leg locus, and also the trip of the primary pump, and also some bypass of the test sections or the blockage of the coolant flow rate. And then you can see the design criteria for the peak cladding temperatures of the four-road models. And both of them, of course, is under the, I mean, in the under the design criteria of the SCWR. But what I'm talking about is you will see that in that case we can perform such transcritical analysis or the safety analysis for the SCWR or the such kind of test loop cooled with supercritical waters. And finally, I will go to the conclusions. And as we talked about, I think the SCWR has a lot of advantages, and but it also have some lot of challenges due to the design geometry and the supercritical, I mean the thermal properties. So that's what's important for the supercritical heat transfer data bank and prediction model is very important. And also the subcritical data bank and also the prediction models is also very important, especially near the critical point. That means the pressure region is from the PWR case to the SWR case. And also, if you want to perform the transient analysis, you have to modification of the system the codes, and then with this code, you can validate by the transcritical experimental data, and also you can perform some safety analysis or some hydraulic analysis of SWR or the field road loops cooled by the supercritical fluids. I think that's it, what I want to show you. And thank you very much for listening. Thank you.
Thank you very much for your very interesting presentation. I think on the next slide we have the upcoming webinars. If we can show just the next slide.
Yeah.
Thank you very much. Thank you for this very interesting presentation. And before we move to the question and answer session, and please, I invite all the attendees, if you have questions, to post them in using the Q&A function, so we can answer them shortly after. Before that, please join us for the upcoming webinars. There will be one that is not listed here at the end of August that will be led by one of the co-chairs and the technical secretary of the non-electric and cogeneration applications of nuclear heat. And then in September, at the end of September, we will have a presentation related to the upcoming report by the Proliferation Resistance and Physical Protection Working Group of GIF on 3S interfaces related to a pebble bed small modular advanced reactor. In October, there will be a webinar on the science for the safe disposal of nuclear waste with a German perspective on this matter. And in November, we will have a webinar, safety-related webinar on severe accidents in SFRs. So please do register for those webinars. There will be soon all the links on the GIF public website to register. Please spread the word about those webinars so they can reach as many people interested in those topics as possible. And with that, I thank you, and I will pass the floor to Patricia to see if we have questions and moderate the Q&A session. Thank you.
Yeah, thank you very much, Alexia, and thank you very much for this interesting presentation, Professor Liu. Right now, I opened the Q&A box, and I do not see any question at all. I need to admit it's a very interesting subject. Probably we talk a little bit less among the 6 Gen 4 reactor system about this one. So a lot to learn for sure. So I have a question. In your opinion, when we see a push really for advanced reactor system on a time frame, when do you think that we will see this type of reactor coming up?
Oh, that's thank you for your question. I think in the beginning of my presentation, I told you that the SCWR is a combination of the PWR, the pressurized water reactor, and the fossil point reactor, point plants. So I think this is it can be a smooth, the smooth extension of the current light water technologies to the supercritical SCWR. And I think this is a very smooth extension. And you see the nuclear power plants is under operation is mostly is the water
Yes.
technology. Yes, and we have a lot of operation experience. For the water reactor technology according to the last 50 years. So I think this is the advantage for the SWR. And also the challenge is also very, the very obviously. And the material effect, it can be avoid so high temperature and high pressure. So I think maybe the most promi promising or maybe the flexible way is we can reduce the temperature a little bit, not so high to the 500 degrees C, but maybe 40, the 450 degrees C or even more lower. And at that temperature, they can also, give a very high thermal efficiency about 40% or maybe 41%. I think even this is very promising because you know that the material is developing. The material research work is still going on. Maybe after 10 years later or 5 years later, we can find a material that's very perfect for the water-cooled reactor technology, and then we can use this material. But in the current, in the current case or in the current time, we can lower the temperature a little bit, and then we can use our water reactor technology and the operation experience for the SWR. That's my opinion. Thank you very much.
Thank you very much. I see one question. Thanks for the presentation. Which countries are interested in supercritical water reactor?
Okay, this is a very good question. If you ask me this question, 10 years ago, I will told you that most of the nuclear countries are very interested in the SCWR. But in the current year, in the recent years after, especially the Fukushima accident happens, the water technology now they worry about the water cooled reactor technologies. And now I think the number of the interested countries is not so large as before. But as I remember or as I see, in my opinion, and I think China, Japan, Europe, Canada is also interested, and even Russia, very interested in developing the SCWR. Thank you. I see another question. May
Yes.
I read it?
Of course, please.
Yes. They ask me what are the main R&D activities besides thermal hydraulics? What are the main challenges? Okay, thank you very much. I think this is not an easy question because I worked with the thermohydraulic points for the SWR. I think except for the thermohydraulic analyze, the design work is very important because you see that they had a lot of advantage for SWR and also it has a lot of challenges. And what's the key points for the SWR, I think, is into the two perspective. One is to design. Yeah, and what I mean the design is to keep the balance between the different effect. Keep the balance from the thermohydraulics, the neutron physics, and the material side. That's what I'm talking about for the last question. Maybe we can lower the outlet temperature. And this work is design work. I think this is very, very important. Or maybe in the top schedule of the whole R&D activities. And then I will say that the material is another important for the SWR, even for the cladding material and also the fuel materials and also the multi-physic and the multi-scale analyze is also important because they have the operation condition is very high and complicated, and in this time the multi-scale and the multi-physical analysis is also important. Thank you.
Yeah, very good. Sorry, I was disconnected. I see another question. Which is better, fast spectrum SCWR or thermal one?
Thank you. I think this is very hard to see which one is better, but I think what you need is to meet your requirements. Which one meets your requirements? Which one is better? For the fastest spectrum, of course, the utilization of the fuel is improved, and then I think at that time the storage of the coolant is reduced. That maybe have some effect on the transient or the safety issues. But for the thermal one, this is it is easy to how should we say to perform the analysis or the manufacturers, but the thermal one can reduce the utilization of the fuel. What's your requirements? Which one can meet your requirements is better, I think. Thank you.
Thank you. I don't see other questions, and I think we answer which country are interested in SCWR. I was disconnected, so my apologies again. Thank you very much, Professor Liu, for this webinar and for answering all those questions. I think we can conclude today, and we'll see you soon at the end of August for the next webinar. Thank you, Alexei, again for your help and support. And again, thank you very much, Professor Liu. I wish you all a good day or a good evening.
Good morning.
Thank you very much.
Thank you.
Bye-bye, everyone.